This question came for EC GATE in 2017 for 2 marks in set 1. The question is, as shown, the figure is shown here, a uniformly doped silicon bar of length L.1 micrometers represented here with a donor concentration Nd is equal to 10 per 16 per centimeter cube is illuminated, light is incident here, at x equal to 0, such that electron and hole pairs are generated at the rate of GL given here, GL naught times 1 minus x by L, where x is in between 0 to L, which means within the semiconductor bar, where GL naught is 10 power 17 per centimeter cube per second. Now, whole lifetime is 10 power minus 4 second. Whole lifetime is given here, which is tau p. Electron charge is given. Hole diffusion coefficient is given, dp, 100 centimeter square per second, and low level injection condition prevails. So this is important point, that low level injection condition prevails. What does it mean by low level injection is when we try to inject extra carriers by incidenting light, in which case the majority carrier concentration doesn't change much. That's what it means. So let's see that thing here. So how many electron hole pairs were generated? That is this generation rate given. So let me substitute the GL naught here. So GL is equal to 10 power 17 per centimeter cube second times 1 minus x over L. Of course, given within this range. Now, this tells per unit time. So we need to find irrespective of time, so that it will be per unit volume. So we need to multiply that with the lifetime of hole. So if we do that, we get 10 power 17 per centimeter cube second times 1 minus x over L times the lifetime, which is 10 power minus 4 seconds. Second cancel. We get 10 power 13 per centimeter cube times 1 minus x over L. What is this value? This is the delta P with respect to x. Why are we talking only about the holes here? Because we have multiplied this with the whole lifetime, and of course low level injection assumption or low level injection condition prevails, which means the minority carriers in this semiconductor are holes, because this is a n-type semiconductor, because donor doping is done. So hole concentration is minority, hence we are talking about only the minority carrier concentration here. Now coming to the continuation of the question, assuming a linearly decaying steady state excess hole concentration that goes to 0 at x equal to L, the magnitude of the diffusion current density at x equal to L by 2 in ampere per centimeter square is dash. Now, to find the diffusion current, first of all, of course, for holes, Jp diffusion, we know the formula, which is given by minus q dp, partial differentiation of p with respect to x, assuming that Pn, because this is n-type semiconductor, of x. Now, let's find what is the hole concentration throughout this semiconductor. So, let me take the x-axis where we have till 0.1 micrometers. This is 0. We know before the illumination, we have some minority carrier concentration, which is the hole concentration, which would be approximately 10 power 4 per centimeter cube, because this is 10 power 16. We know Ni square is 2.25 times 10 power 20. 10 power 20 minus 16 would be 10 power 4. Ni square by Nd. So this value would be somewhere around 10 power 4 approximately. Now, because of this generation, how much is the carrier concentration at x equal to 0? That is 10 power 13 per centimeter cube, which is very, very high compared to 10 power 4. So let's say that value is somewhere here. This is delta P. Delta P n of 0, which is equal to 10 power 13 per centimeter cube. Now when we substitute x is equal to L, this becomes 0. 0 times anything is 0. So we get 0. Now of course, if you look at this variation, it is linear. Hence, this would be linear. Now let's say this is L by 2. midpoint. Now assuming this linearly decaying steady state excess hole concentration, this is excess hole concentration linearly decaying from 0 to L. Then we need to find the diffusion current. Of course, looking at this line, the slope at L by 2 or here would be same. It doesn't really matter where we take the slope because it's a line. So we need to find the slope. So for that, this value can be written as y2 minus y1 over x2 minus x1, which is equal to y2 is 0. I am not taking this minority carrier concentration under equilibrium because anyway when we subtract it goes away. So y2 is 0 minus 10 power 13 per centimeter cube divided by x2 is 0.1 micrometers minus 0. This value would be minus 10 power 13 per centimeter cube divided by 0.1 times 10 power minus 4 centimeters. This value we can write is equal to minus 10 power 18 per centimeter power 4. Here we can multiply with 10 and 10 power minus 1. Hence it becomes 10 power minus 5 times 1. Take it above, it becomes 10 power 18. So this is the value of this differentiation. We found the slope. Now all we have to do is substitute Q, dP and this value to find what is Jp diffusion. So let me do that here. So Jp diffusion is equal to 1.6 times 10 power minus 19 coulombs. Q value, of course there is a minus sign, times dP is 100 centimeter square per second, times there is a minus sign here, the slope, minus cancel, 10 power 18 per centimeter power 4. We can cancel centimeter square, it becomes square, 10 power 18, it becomes minus 1. This minus 1 we can take it here, so 1 0 goes off, minus 1 goes off. We are left with 1.6 times 10, that is 1.6 times 10 is 16. Coulomb per second is amperes per centimeter square. This is the Jp diffusion, which is 16 ampere per centimeter square. The value we are supposed to take in this blank, the answer is 16. Of course here they have asked the magnitude. The magnitude of this positive value is anyway positive, which is 16. But a point to remember is the current that is flowing here, the reference direction was in positive x. In case in a different question if they ask you direction, of course the current is flowing in positive x direction. And the value here is 16 amperes per centimeter square.